Can you hear me?
white bucket.
Dear students, can you hear me?
Yes,
Yes, sir.
Yes, sir.
Yes, sir. Yes.
Thank you. So, and can you see the screen well?
Yes, sir.
What is written on the screen?
Isolation constant of weak acids.
Very good. So, yes, let's start with. Let us study about the ionization constant first. So here we have here we are going to study about the ionization constant. This ionization constant of weak acid. A weak acid HX that is partially ionized is the aqueous solution. The equilibrium can be expressed by the equation HX plus H2O, that is H3O plus X minus. Now we know that the initial concentration is C mole per liter and the initial concentration for this H3O plus and OH minus is 0,0. Now if alpha is the degree of dissociation or extent of ionization, change in the concentration would be minus C alpha for the reactant one, and it would be and the concentration or change in the concentration for the products will be plus C alpha and plus C alpha, and thus the concentration of the concentration at equilibrium, as the initial concentration was C, now the change has been made, which is minus C alpha, and the initial concentration was 0, but the change is plus C alpha, so total 0 plus C alpha and 0 plus C alpha for the product, and for reactant C minus C alpha. If we take C common, we get 1 minus alpha, C into 1 minus alpha, and for the products we have C alpha, C alpha. This is how do we understand, my dear students. So here C is called the initial concentration of the undissociated acid HX at time t is equal to 0, and alpha is equal to the extent up to which the HX is ionized into ions. So using this information, we write the equilibrium constant. Let us see how do we write the equilibrium constant. K is equal to, here we write the equilibrium constant. K is equal to concentration of H3 plus divided by concentration of X minus, concentration of H3 plus multiplied by the concentration of X minus divided by the HX, concentration of HX and concentration of H2. We are well aware that the concentration of water in liquid state, we consider it as a constant, and that is why multiplying the concentration of H2O with K, we get K into H2O, that is equal to H3O plus multiplied by X minus divided by HX. Thus, if we write for K into H2O, if we write Ka, then here we call Ka is the dissociation constant or ionization constant for an acid, and thus we can write Ka is equal to concentration of H3O plus into concentration of X minus divided by HX. That is equal to concentration of H3O plus is C alpha, X minus is C alpha, and divided by C into 1 minus alpha. So we will get C square alpha square divided by C into 1 minus alpha, and thus finally we get K is equal to C alpha square divided by 1 minus alpha. Now for weak acids, the degree of ionization alpha or degree of dissociation alpha is very small as compared to 1, and that is why 1 is quite greater than alpha, and if we take 1 minus alpha is equal to 1, I repeat, if we take 1 minus alpha is equal to 1, so by taking 1 minus alpha is equal to 1, we get Ka is equal to C alpha square divided by 1, and finally we get Ka is equal to C alpha square, and therefore alpha square is equal to Ka by C, and therefore alpha is equal to square root of Ka by C, or we can say that Ka is equal to C alpha square. For very small value, please remember that this equation we can write it for very small value of alpha, where 1 minus alpha is equal to 1, my dear students. So now we want to study about Ka. We know that Ka is known as the dissociation constant or ionization constant. Once again, you can read it from here that Ka is called the dissociation constant or the ionization constant for an acid. So at given temperature, K is the measure of the strength. K is the measure of the strength of the acid HX. Larger the value of K, stronger is the acid. So the strength of an acid depends upon the value of K. The more is the value of K, the more stronger the acid would be. K is dimensionless quantity with understanding that standard state concentration of all species is 1 mole per liter. So we can say, being constant, it should be a dimensionless quantity. Now, please remember that negative logarithm of Ka is also called pKa. So here, this negative logarithm of Ka will be considered as a pKa, my dear students. Here you can understand this equation. Please remember it. It's a pKa for we people. Now let's move forward. Now we have a question to study, my dear students, that the ionization constant of HF is 3.2 into 10 to the power minus 4. Calculate the degree of dissociation of HF if concentration of HF solution is 0.02 molar initially, and then calculate first the concentration of all species present at equilibrium, and second, concentration of pH of the solution. So let us move forward and understand. Here, my dear students, the ionization constant for acid Ka, the value is clearly given, which is 3.2 into 10 to the power minus 4, which is quite greater than 1 into 10 to the power minus 14, which is our Kw. So let's say, compared to self-ionization of water, dissociation of water is primary reaction, and that is for when we add HF to water, it gives us H3O plus and F minus. So initially the concentration of 0.02, which is, we represent it as a C, that, and the concentration of products is 0 and 0. Now let us see what change takes place when the equilibrium is established. So when the equilibrium is established, my dear students, we know that the concentration of reactant decreases. So if alpha is the degree of dissociation, then the decrease in concentration would be C alpha, and decrease in concentration of reactant would be C alpha, but increase in concentration of product would be plus C alpha and plus C alpha. So here the concentration decreases, that is why we put negative sign. Here the concentration increases, that is why we put positive sign, my dear students. So this is how we understand the negative and positive sign for the change. Now the total concentration was C, and the new concentration is C minus C alpha. And here the total concentration was 0, so it is 0 plus C alpha, and for F minus also it is 0 plus C alpha. So here C is 0.02, so we can write, instead of C alpha, we can write 0.02 alpha or 0.02 alpha for the products. And finally, if we write the equilibrium, if we write the concentration at equilibrium, the concentration is equal to 0.02, which was the initial concentration, minus 0.02 alpha for the reactant HF, and the concentration of H3O plus is 0.02 alpha, 0.02 alpha. Remember that this alpha is nothing but your degree of dissociation, my dear students. So now finally what we come to know is 0.02 minus 0.02 alpha is equal to 0.02 into the bracket 1 minus alpha. Thus, my dear students, we write Ka is equal to the concentration of H3O plus into F minus divided by HF. The concentration of H3O plus you can see here, it is a 0.02 alpha. The concentration of F minus is also 0.02 alpha divided by the concentration of HF, which is written over here 0.02 into 1 minus alpha. So let us put these values, and we are well aware that 0.02 divided by 0.02 gives us 1. This alpha and alpha becomes alpha square. I'm talking about them. This alpha and this alpha become alpha square, and we have, so we can uh, change it this way, and we will have 0.02 into alpha square divided by 1 minus alpha here, which is having the value 3.2 into 10 to the power minus 4, my dear students. So as we move forward, my dear students, what happens? The alpha square divided by 1 minus alpha is equal to 3.2 into 10 to the power minus 4 divided by 0.02. That is equal to alpha square divided by 1 minus alpha is equal to 3.2 into 10 to the power minus 4. For 0.02, my dear students, we write 2 into 10 to the power minus 2. So ultimately it is alpha square divided by 1 minus alpha. Now when we do this division, 3.2 divided by 2, it will give us the 1.6, and 10 to the power minus 4 divided by 10 to the power minus 2, that is 10 to the power minus 4 plus 2. So alpha divided by 1 minus alpha is equal to 1.6 into 10 to the power minus 2. Therefore alpha square is equal to 1.6 into 10 to the power minus 2 into 1 minus alpha. So by doing this or opening this bracket, we will get 1.6 into 10 to the power minus 2 minus 1.6 into 10 to the power minus 2 multiplied by alpha. So now by writing the this equation in the form of the uh, ax square plus bx plus c is equal to 0 form quadratic equation, we will write alpha square. Now the species which are on the right side of the equal to sign, they are brought to the left hand side, so their sign changes, and what we get is alpha square plus 1.6 into 10 to the power minus 2 alpha minus 1.6 into 10 to the power minus 2 is equal to 0. By solving this equation, we will get the value of alpha. This value, you know that we can solve the quadratic equation by using the root formula minus b plus or minus square root of delta upon 2a. So using this, we will get the value of alpha is equal to plus 0.12 and alpha is equal to minus 0.12. My dear students, this value what we get, the negative value is not of any use, so the negative value is not acceptable, and hence we will have alpha is equal to 0.12. This means that degree of ionization, that is alpha is equal to 0.12, then the equilibrium concentration of other species, for example HF, F minus and H3O plus are given by, so let us we know that this concentration of the other species are represented in the form of alpha. So we know that concentration of H3O plus and concentration of F minus is equal to C alpha. You can see here in the equation, my dear students. Yes, you can see here that the concentration of H3O plus was considered to be 0.02 into alpha. The concentration of F minus was also considered as 0.02 alpha, and the concentration of HF was considered to be 0.02 into 1 minus alpha. So on the basis of this, let us understand, my dear student, here we put these values that the concentration of H3O plus and F minus is equal to C alpha. We know that the value of C is 0.02 and alpha is 0.12. So ultimately we get the concentration 2.4 into 10 to the power minus 3 molar. The concentration of HF is equal to C into 1 minus alpha, that is 0.02 into 1 minus 0.12, that gives us 17.6 into 10 to the power minus 3 mole per liter. So now, my dear students, we want to find out pH. pH is equal to minus log of H plus. We have calculated the concentration of H plus here, which is the concentration of H3O plus, and that gives us the value 2.4 into 10 to the power minus 3. So the same value we put here for the concentration of H plus, that is 2.4 into 10 to the power minus 3. We know that log of x plus y is equal to x into y is equal to log of x plus log of y, and log of 10 is equal to 1, and 10 to the power log of a raised to x is equal to x log a, log of 10 is equal to 1. So this value minus log of 10 to the power minus 3 is plus 3, and log of minus log of 2.4 is minus 0.38, and finally we get the pH is equal to 2.62. So this is how, my dear students, we can solve all the problems. Now if you have any doubt, you can ask me. Dear students, whatever I have explained, now if you have any doubt into it, you can ask me.
Sir, can you please explain the example or a problem?
You need to speak it again. I am not able to hear you. Can you please speak once again?
Sir,
Maitri,
please explain us example one more.
which example once
Sir,
more, beta?
please explain us. Yeah.
Can you repeat, please?
Please explain examples one more.
The same example, I need to explain it once again.
No, sir. Another, because I was
Okay, no problem. We
confused.
have the next example. Don't worry. Yeah, anyone else? See, this is the next example or next problem we are going to solve. So let us understand about this. Let us look at the question or the problem here. The pH of 0.01 molar monobasic acid is 4.80. The pH of 0.01 molar monobasic acid is 4.50. Calculate the concentration of species H plus, A minus and HA at equilibrium. Also determine the value of Ka and pKa of the monobasic acid. So here we are given the initial concentration C 0.1 molar, that is the concentration of monobasic acid, and pH is already given as 4.5. Now we know that if we have an acid HA, that will dissociate and give us H plus and A minus. Now we know that the initial concentration C is 0.01 molar. So the initial concentration is 0.01 molar, and initially there are no products formed, so their concentration is 0 and 0. Now suppose the change in the concentration, as we know that when the reaction takes place, the concentration of reactant decreases. So the concentration for reactant HA decreases to C alpha, and the same amount of product is formed, which is C alpha and C alpha. So we can write 0.1 minus C alpha is equal, and for the products we get C alpha and C alpha. In some of the cases, you can just take X instead of C alpha. So instead of C alpha, you can write X, but I have written C alpha. You consider it as a one letter, and we can solve it. Now we want to find out the concentration of H plus, that is, we want to find out the value of C alpha. We want to find out the concentration of A minus, that is also the value of C alpha. And we want to find out the concentration of HA, that is 0.1 minus C alpha. So now let us find this. We know that concentration of H plus is equal to C alpha, pH is equal to minus log of H plus, and C is equal to 0.1. These are the values, or this is what we have tried to understand the question, my dear students. Now let us solve the problem. Now we know that pH is equal to minus log of H plus. So the value of pH is equal to minus log of H plus. We know that pH is equal to 4.5, and minus log of H plus we can write. So therefore H plus is equal to anti-log of minus 4.5. Instead of 4.5, my dear students, we can write minus 5 plus 0.5. So this is what it is, the antilog of minus 5 multiplied by the antilog of 0.5. Now antilog of 0.5 is 3.16 and antilog of minus 5 is equal to 10 to the power minus 5. So please remember that antilog of any number is equal to the 10 to the power that particular number. So antilog of minus 5 is equal to 10 to the power minus 5 and antilog of 0.5 is 3.16 and therefore the concentration of H plus is equal to 3.16 into 10 to the power minus 5. Now we know that at equilibrium the concentration of H plus and A minus are same, and that is why we have the concentration of A minus is equal to 3.16 into 10 to the power minus 5. Now we want to calculate the concentration of HA, that is 0.1 minus C alpha. Now C alpha is very small, which is 3.16 into 10 to the power minus 5, which is approximately is equal to 0.1 only. So here we can calculate the various values. Now we want to calculate the Ka. So we know that Ka for any equation is equal to the product of products divided by the concentration of the reactant. So we will write H plus, concentration of H plus multiplied by concentration of A minus divided by HA. That is, we put the value of this concentration. The concentration of H plus is 3.16 into 10 to the power minus 5. The concentration of A minus is also 3.16 into 10 to the power minus 5. And the concentration of HA we have just calculated is equal to 0.1. So we will put these values, and by doing the simplification we can find the value as 1 into 10 to the power minus 18. So now we know that pKa is equal to log of Ka. So here pKa is equal to log of Ka. The value of Ka given is 1 into 10 to the power minus 8. So it is minus log of 10 to the power minus 8, which we get it as 8. So here we can find out the various answers, that we wanted to find out the concentration of H plus, we wanted to find out the concentration of A minus, and we wanted to find out the concentration of HA. We have done it. Apart from that, we have found out the value of Ka as well as the value of pK also have been determined by us. So you can see that this is the value of, my dear students, this is the value of Ka, and this is the value of pKa that we have found out. Maitre, do you have any question? Do you understand, child? If not, then we have even the another problem. Now let us move forward and understand the next question. Calculate
I understood
the
it.
pH of 0.08 molar solution of hypochlorous acid, HOCl. The ionization constant of the acid is 2.5 into 10 to the power minus 5. Determine the percentage dissociation of HCl. So let us here determine the percentage dissociation. So first of all, we should know this formula, that percentage dissociation is equal to the concentration of HA dissociated divided by the initial concentration of HA multiplied by 100. But this is the value of alpha, my dear students, which we call it as a degree of dissociation. So we can write it alpha multiplied by 100. This is the simple formula to calculate the percentage dissociation. Now we know that for acid HOCl, we can write the dissociation equilibrium, and that is what HOCl plus H2O, that gives us H3O plus and ClO minus. Initial concentration of HOCl is given, which is 0.08 mole per liter, that you can see it from the question itself. The initial concentration is, calculate the pH of 0.08 molar solution of hypochlorous acid. So the initial concentration has already been given, my dear students. We know that initially no products are formed, so their concentration is 0 and 0. Now the change in the concentration. We know that the concentration of reactant changes or decreases so that the products are formed. So when the reactants are utilized, when the reactants decrease their concentration, the products are formed. So that is why the change in reactant is negative, whereas change in product is positive. Now, my dear students, we know that if we have alpha is equal to degree of dissociation and C is the initial concentration, then we can write the change into the concentration is C alpha for the reactant, and the same amount of product is formed because their stoichiometric coefficient is 1 in both these cases. So we will write it as C alpha, and C alpha amount of product has been formed. Now at equilibrium, what happens? The initial concentration was 0.08. The concentration has been changed by C alpha, so it becomes minus C alpha. And here the concentration of H3O plus is 0 plus C alpha, that is C alpha. Here the concentration of 0 plus C alpha, that is C alpha. Now for the dissociation constant Ka, we write the product of the concentration of product divided by the concentration of reactants, and that is why we write H3O plus, concentration of H3O plus multiplied by the concentration of ClO minus divided by the concentration of HOCl. We know that the concentration of H3O plus is C alpha. You can see here the concentration of H3O plus is C alpha, concentration of ClO minus is C alpha, and concentration of HOCl is C 0.08 minus C alpha. So let us put these values. That is equal to the value of Ka is already given into the question, which is 2.5 into 10 to the power minus 5. Now let us say C alpha is equal to x. So we will write x into x, that is x square divided by 0.08 minus x is equal to 2.5 into 10 to the power minus 1. Now for weak acid, we know that for weak acid the degree of dissociation is very small as compared to 0.08. So we will write 0.08 is greater than x, and that is for 0.08 minus x is approximately 0.08. So instead of 0.08 minus x, here we write 0.08. So we will have x square is equal to 0.08. X square divided by 0.08 is equal to 2.5 into 10 to the power minus 5. Now, my dear students, let us solve this problem. So, as we know that x square is equal to 2.5 into 0.08, that is 2.5 into 10 to the power minus 5 multiplied by 8 into 10 to the power minus 2. For this, we have written it this way. That is equal to, see, 25, 8s are 200, and 10 to the power minus 6, 10 to the power minus 2 is 10 to the power minus 8. So thus we have the x square is equal to 2 multiplied by 100 into 10 to the power minus 8. So x is equal to square root of 2 into 100 multiplied by 10 to the power minus 8. We know that square root of 2 is equal to 1.41, and therefore your x is equal to 1.41 for this square root of this. Square root of 100 is 10, and square root of 10 to the power minus 8 is 10 to the power minus 4, and finally we get x is equal to 10 to the power x is equal to 1.41. 10 multiplied by 10 to the power minus 4 will give us 10 to the power minus 3. This is what it is, your C alpha. So now we have the value of C alpha, percentage dissociation. Then, my dear students, HA, that is dissociated divided by HA initial multiplied by 100. That is what we want to find out to know the percentage dissociation. And that is why we write the SS dissociated is C alpha, because total C alpha HA has been dissociated. That is what it is, the change in the concentration divided by the initial concentration. We can write it as a 0.02 into C minus C alpha multiplied by 100. So we can write x multiplied by 100 divided by 0.08 minus x. Here I think I have made a mistake, my dear students. Instead of writing 0.0 C minus alpha, we just need to write 0.08. So even 0.08 minus C alpha, we take it 0.8. So finally we get x multiplied by 100 divided by 0.08. What is the value of x? The value of x we have already calculated as 1.41 into 10 to the power minus 3. So we will put this value for x, 1.41 into 10 to the power minus 3 divided by 0.08, and finally we get the answer as 1.76%. Now we have got the concentration of H plus, my dear students, because we know that the concentration of H plus here, the concentration of H3O plus is nothing but your C alpha, and the value of C alpha, that is equal to x, we have got it here. The value of C alpha is, or value of X is 1.41 into 10 to the power minus 3. So we can find out the pH, my dear students. So when we want to find out the pH, pH is equal to minus log of H3O plus, that is minus log of 1.41 multiplied by 10 to the power minus 3, that is minus log of 1.41 plus minus log of 10 to the power minus 3. We know that minus log of 10 to the power minus 3 is 3, log of 1.41 is 0.15. So by doing simplification, we can find out the pH is equal to 2.85. Maitri, now you understand? Maitri?
Yes, sir. Thank
Okay,
you.
welcome. So this is how, my dear students, we move forward and solve the problems. By solving this problem, you can understand the concept exactly. Now, my dear students, let me explain one more thing to you, my dear students. I think this is what it is required to be explained once again. Um, See, dear students, whenever we are asked to find out the percentage dissociation, we have this formula for the percentage dissociation. Our percentage dissociation is equal to HA dissociated divided by HA initial multiplied by 100. So if you look into this HA, the HA dissociated is C alpha because initial concentration was 0.08. C alpha was the dissociation of the acid. So you can put here that acid dissociated is your C alpha, acid initial is your C, please remember, and then it is multiplied with 100. So you can write multiplication with 100. Now simply when you cancel this C and C, my dear student, you get alpha into 100, and that is why I have written it clearly, alpha into 100. Here also when you look into the solution of the problem, you can find out that your X is equal to C alpha, your X is equal to C alpha multiplied by 100, this is multiplied by 100, and then you have this C, which is the initial concentration, 0.08, it is already given. So when you solve this problem, you actually multiply this alpha with the 100. So I hope you understand, my dear students, that the percentage dissociation is nothing but the degree of dissociation multiplied by 100. Now, my dear students, the time is very less for us, so uh, let us even understand the ionization of the weak acid. The ionization of base MOH can be represented by the equation MOH that gives M plus plus OH minus. In a weak base, there is a partial ionization of MOH into M plus and OH minus. The case is similar to that of acid dissociation equilibrium. The equilibrium constant for base ionization is called the base ionization constant. Base ionization constant is represented by Kb. So as it was for acid, we wrote Ka. As it is for base, we will write Kb. It can be expressed in terms of the concentration in molarity of the various species in equilibrium by the following equation. So Kb is equal to the concentration of M plus divided by concentration of OH minus, concentration of M plus multiplied by the concentration of OH minus divided by MOH. Please remember, my dear students, that if you look into this equilibrium, if you look into this particular equilibrium, here we have not used water at all, and that is why we can directly write the Kb in this form. But please remember that your Kb is nothing but the equilibrium constant. Your Kb is nothing but the equilibrium constant K multiplied by the concentration of water. Please remember that your Kb is equal to the equilibrium constant K multiplied by the concentration of water. That is what it gives us Kb. So our Kb is this. So even the water, like in the equilibrium, if they have written water, then please do not mention water in case of the calculation of the Kb. Here alpha is called the degree of ionization, or for base, or it is also known as the degree of dissociation for the base. When equilibrium is reached, we can express this equilibrium in this form. So this is the base which is ionized into M plus and OH minus. Same way, my dear students, the initial concentration is C, but initially there are no reactants available. The change that takes place in reactant is minus, but the change that takes place in product is plus. The change in reactant is minus C alpha. The change in product is C alpha and C alpha. See, we write C alpha because the stoichiometric coefficient for this ion is 1. So we will write C alpha, C alpha. If the stoichiometric coefficient is 2, we will write 2C alpha, 2C alpha. If the stoichiometric coefficient is X, we will write XC alpha, XC alpha. If stoichiometric coefficient is N, we will write NC alpha, NC alpha. Now here also the stoichiometric coefficient is 1. So we will write minus C alpha. If the stoichiometric coefficient is 2, we will write minus 2C alpha. If the stoichiometric coefficient is N, we will write minus NC alpha. Please remember and understand it well. Now, my